afternoon. Welcome everybody to this new webinar series, The Importance of Being H.P.C Earnest, which is a new remote and interactive initiative that we have decided to put forward to bring the CCAM community together around topics of broad and timely interest in these extraordinary times that we have to endure. So we already organized a previous series that was more focused on the computational challenges that brought COVID itself. In this occasion, we want to create a forum to analyze and discuss the opportunities for leading edge science that are enabled by extreme scale readiness of codes, data repositories, and data analytic tools. All this in the framework of the new generation of H.P.C facilities and the coming generational challenges posed by the exascale that will be deployed hopefully in next years, pretty soon. So in the spirit of CCAM, we want to address these challenges, emphasizing the opportunities for science and the central role that codes and algorithmic developments play in this challenge. And to this end, we have invited leaders of outstanding projects in Europe and the USA, of initiatives and institutes and community projects that focus on the development of community-wide software and data-driven science. So we have organized this series of webinars into 5 different sessions where we bring together initiatives that cover complementary areas that are relevant to CCAM communities in order to favor a transversal and interdisciplinary dialogue. The structure of these sessions will take around 2 hours, and it will be composed by 3 presentations. So we have 3 different type of initiatives each session. And at the end of these 3 presentations, there will be a common session for questions and discussion. So you can pose questions during the presentations by directly in the YouTube channel. You have the possibility to write or interact, so you can pose your questions directly there. And then Sarah Bonella, Deputy CCAM Director, and myself will be taking care of collecting these questions, and then we will be guiding sharing this discussion session afterwards. Again, the questions that you pose can be either specific to the science that speakers will be presenting about their initiatives, or also any kind of question that you want to bring that can be more transversal or open to them, so that then also during this discussion session, we will favor the possibility that our invited lecturers can just talk to each other and create a more relaxed and dynamic atmosphere. So any question will be welcome. If you have problems posing the questions directly through the YouTube channel, you can at any time directly email me at the email address director@ccam.org. So director@ and then ccam.org. And then again, we will be collecting them and then prepare the corresponding discussion at the end of this session. So in order to move on for today's session, so it's a pleasure for me to introduce 4 outstanding scientists that are leading a very relevant and in this case also complementary initiatives in their type of and goals. So the one we have Nicola Marzari, who is the director of a National Center of Competence in Research called MARVEL. This is a Swiss initiative that's funded by the Swiss National Foundation and brings together research and institutions across the country to create a center on computational design and discovery of novel materials, MARVEL. And basically the vision or the goal of this project is to accelerate the design and discovery of novel materials through the materials informatics platform of database-driven high-throughput computing. So I'm sure we will hear about that. We also have with us Claudia Filippi and Antonio Schemama from University of Twente and Toulouse. They are leading a recently started Center of Excellence. These are initiatives that are promoted by the European Union with the goal of develop and implement and disseminate the development of codes and software that is ready to exploit, to run in the exascale and exploit the machines, the new supercomputers that the European Union is pushing to deploy in the coming years. So this particular Center of Excellence, the acronym is TREX, aims to federate scientists, H.P.C experts, and small enterprises to unite fragmented efforts in an integrated software platform with the aim of develop, promote, and maintain open source exascale-ready software solutions in quantum chemistry. Actually, the name of the COE is Targeting Real Chemical Accuracy at the Exascale. And I'm sure that this is at its beginning, but we will have the opportunity to know what are the challenges and what is the new science that these efforts will make it possible. And finally, we have also, it's a pleasure to welcome Julia Galli from the States. So this is a US initiative. So Julia is at the University of Chicago, and she is leading a MICON, Midwest Integrated Center for Computational Materials. This is one of a series or a set of institutes that are funded by the DOE with the idea also again of pushing forward the development of scientific software in the environment of H.P.C. And the particular goals of MICON are to develop and disseminate interoperable open source software, data, and validation procedures for functional materials. So, and again, I'm sure we will listen about what are the goals. So I thank you for accepting to come to this session and to share with us your insights. So without further delay, I think now it's a pleasure for me to give the floor to the first speaker, Nicola Marzari. So Nicola, now it's your turn.
Thank you, Ignacio. Great pleasure to be here virtually with all of you. And I'm particularly happy to be here with Julia, Claudia, and Anthony. It's very exciting. Since I was the first speaker, I took the liberty of taking a broader view on the entire field and talk about what I think is the great mystery of computational science and what are the opportunities. So let me start from this. You probably recognize this. This is Sharbat Gula. It's one of the most iconic pictures of the 1980s took by Steve McCurry in one of the Afghan refugees camps. And not only it's a famous picture, but it was taken with the most famous film ever, Kodachrome. Kodachrome was made by Kodak, the giant of the film industry during the 20th century. And in 2013, Kodak sold basically all of it to Apple, Google, Facebook, Amazon, Microsoft, and so on. So this was the first statement. The second statement, equally beloved, is here. This is the Encyclopedia Britannica. I actually am very proud. I have two sets of volumes, but I think these days there are very few parents that give the entire 32-volume set to their children. And the last example actually comes courtesy of Elisa Molinari. So last month, Zoom has reached a market capitalization that is larger than the top 7 airlines in the world combined, so $48 billion. And just on the demise of this, I'll add also, for those of you probably that are in the States, Blockbuster and Borders. And so this introduction caps my first fortune cookie that is here, and say underestimating digital is not good for you. I mean, these are all enterprises that suffered because of this. So what about digital in science? You all know this, this picture comes from the Top 500 conference. It shows us the capability of the most powerful supercomputer in the world, that's in red, or the aggregated capability of the Top 500, that is in blue. And basically, we have been on a doubling of capacity, or I started calling 100% growth whenever I sort of talk to any investor. That sounds very good. Every 14 to 16 months. And that really means that in 30 years, something like a calculation that took 1 year would just took 1 second. And this is just with digital classical computing, and neuromorphic computing might be relevant. I think we'll hear later about qubits and quantum computing that might be even more disruptive paradigms. What is the result of all of this? Well, you know, computational science, of course, relies on this H.P.C. infrastructure, and the impact of computational science is now extremely widespread. This comes from 6 years ago in Nature, looking at the most cited papers in the entire history of science, engineering, medicine, and biology, and actually remarkably showing that the most represented field in the top 100 most cited papers ever is actually computational quantum mechanics, in particular density functional theory. 2 papers in the top 10 and 12 in the top 100. And that's even more remarkable when we look at the physical sciences, in particular condensed matter physics, material science. This comes from an exercise I do periodically. The data here are from last year, looking at the journal from the American Physical Society, Physical Review Letter, and so on and so forth, with a great focus on condensed matter physics. And you see the top 20 papers are overwhelmingly dominated by computational quantum mechanics, in particular density functional theory. There is one paper from Moller and Plessé on Hartree-Fock, and you would need to go, say, beyond the top 20 to find, say, Bardeen, Cooper, Schiffer Nobel Prize for superconductivity. So this is just to say how relevant, how prominent is the impact of computational science, and I call it digitalization in science, is clearly here. The question that is interesting for all of us is, what are we doing about this? So if for a moment you remember that list from the American Physical Society, the most cited paper ever in the physical sciences in that society. And now I go to another institution I'm extremely fond of, is the European Research Council. That's a European body that really awards research grants for excellent science. And I take the categories from condensed matter physics. So this is how the world of condensed matter physics is organized. And, you know, remarkably, there is nothing even remotely that resonates with, you know, computational quantum mechanics, electronic structural methods, and so on and so forth. So this is just to say, you know, how much still road there is to travel to try and get these concepts embedded in policymakers. Now, my last 2 slides on this topic, I mean, take them with a grain of salt. I hope SECAM is not recording this, but it's just taking, you know, a broad view again from a European perspective. In this case, these are the numbers that I had about what are major funding and major initiatives for infrastructure in the physical sciences. So we go from the European Space Agency. It's sorry, I changed the billions. It's sometimes euros, sometimes dollars, sometimes Swiss francs, but roughly the same thing. So 6 billion a year. ITER for fusion. There is a little bit of debate if it's 22 or 65 billion over 28 years. Or CERN, just here, the neighbors, you know, a lot of Nobel Prizes, 1.3 billion francs per year. And now this is, I'll go fast on this, but I'm comparing here Quantum Espresso with CERN. So Quantum Espresso is an open source software, many of you know, for simulation of materials. Actually, I think the most used one that is open source. These are the number of publications per year that comes from Google Scholar. And in particular, if we look at the Web of Science, we have 2,300 articles just in 2019 that was made possible thanks to this. And I think of this not anymore as a piece of software, but as an entire scientific infrastructure. CERN has 944 articles. Of course, it's a completely different discussion and debate, but I sometimes wonder if from the point of view of a society, we shouldn't dedicate 1% of what we dedicate to all this major installation and infrastructure for actually a software and a scientific simulation infrastructure that I think these days is at the very least as important as everything else that we do. And of course, we are here because there is actually progress in this. I mean, we all lead different centers funded by the European Union, in my case, funded by the Swiss National Science Foundation, funded the Department of Energy. So I think there are significant improvements in this direction. But I think the numbers versus the impact is still quite staggering. Now, in our own field, why is this relevant? Actually, I'd forgotten the fortune cookie number 3. That is, at the end of the day, notwithstanding all that is happening, I don't think we are doing much in terms of thinking what is needed to support and to nourish the kind of infrastructure that we need for computational science. And the reason of why this matters is not only in the numbers that I was showing below, but because more and more, not only we believe, but we start seeing how much what is done in this computational material science, computational chemistry, computational condensed matter physics is actually relevant for society. And this is a nice summary. I think it uses the materials revolution term that is the slogan of our center, but this comes from Baron, is a technology publication in the United States, and says, you see, we are in the midst of a material revolution. Powerful simulation techniques combined with increased computing power and machine learning are enabling researchers to automate much of the discovery process, vastly accelerating the development of new materials. And materials are incredibly relevant for the society well-being. I mean, we need novel materials to find a more efficient way to harvest energy, say to transform solar energy into electricity or solar energy into fuel, or to store that energy, both a large scale for the grid or at a smaller scale, maybe for transportation, maybe for what we do every day. But it's not only energy. I mean, the cost of food and our capability of manufacturing is directly related to energy. And we want materials to, improve our impact on the environment. We want material that can lighten the load of what we do, from materials for transportation to materials for communications. And so novel materials these days are considered, as you see it, one of the $1 trillion markets. The other two, by the way, are, according to Baron, CRISP-9, genetic editing, and machine learning. Now, the fact that we can use simulations to predict materials, I think has been clear for 40 years. There is nothing new under the sun. I love this picture done by Marvin Cohen 40 years ago, showing, I would say, more or less for the first time almost, that you could really predict material properties using computational quantum mechanics. In this case, the phase stability, the equilibrium lattice parameter of silicon, or the pressure at which it would make a transition from the diamond structures to the beta-tin structure. Of course, other things have happened. One that I'm very fond of, and I think this is the first time I had heard about this when Jens Noskov gave a talk at MIT, is really using this capability to do predictive, accurate quantum mechanical calculation in reliable and reproducible ways. This will come up later, and showing that one could actually do high throughput searches, in this case looking at 4-component alloys out of 200,000 possibilities that could be ideal for certain target properties. So we have accurate first principle calculation, the capability to do them in an automated high throughput way. And these days we talk a lot about machine learning and the capability of actually learning from our calculation. And actually also started a long time ago. I'm fond of also a couple of papers that I'm showing here, one by Ercolesi and Adams, that were showing already in 1994 how the massive amount of microscopic data that DFT calculation are producing could be used to learn something. At the time, it was interatomic potential, so we didn't have these ideas coming from neural networks or kernel regression methods. This is another work I'm very fond of by Alessandro De Vita and Gabor Shani and Mike Payne that really, was taking the next step in really incorporating all the massive amount of data to accelerate our capabilities to do calculation. And this, in many ways, will be our 3 pillars for material discovery: ab initio calculations, high throughput calculation, and machine learning. And with this, we want to try and explore the space of materials, find novel materials, or find novel properties for well-known materials. What are the challenges there? As you can see, I like to simplify things in lists. I mean, it's a bit like the David Letterman of science. And this is my favorite list. And I think probably we'll hear in the next talk about accuracy. So our simulations need to be accurate enough to make sure that they can predict the right thing. And that can still be very challenging. It's a very tough problem. I will leave exactly the second talk to this. I'll show you a few examples instead of what we have achieved in computational material science in terms of capturing the complexity of the real world, the complexity of real materials and real devices. And then maybe I'll hint, I will not be talking about machine learning or big data, but I'll be talking about the IT infrastructures that we want to have to power all of this. So if we want to talk real world, and we are starting from electrons and atoms, there are 2 directions that I can summarize. One is to look at complex systems. Here I'm just showing a picture from Ismail Adabo about computational electrochemistry. That is, a nice problem where you can adopt multi-scale approaches, where you do quantum mechanical simulation in a mesoscale formulation, maybe treated in this case with Poisson-Boltzmann equation. Or, we can address not the complexity of the system, but the complexity of the process. That's very typical of spectroscopic properties. I'll show you a few examples from transport. So the complexity of size, again, would require either multi-scale approaches or maybe the efficient exploration of the configurational or conformational complexity of materials. And again, a lot has been done in the last 10, 15 years on sampling techniques like metadynamics, and all the derivatives from that have really increased our capability to explore phenomena that are rare and difficult, like nucleation and growth. Here I just show a small example that I mean, for us, it was an application, again, came from these ideas that Gabor Shani has developed, in this case, not so much a neural network, but kernel methods. Here we just tried out ferromagnetic iron, and this is showing how, how well you can represent the dynamics, in this case, the phonon dispersion of a material when you compare density functional theory with one of these Gaussian approximation potential. But what is relevant is that these, provide an accelerator on length scale and time scales, preserving density functional theory accuracy. So with that accuracy, now you can study tens, hundreds of thousands of atoms, and you can address processes that are beyond brute force density functional theory simulation, in this case applied to structural materials, and looking at how you could have a king pair nucleation and propagation, again in BCC ferromagnetic iron, something that one would never be able to do with direct density functional theory simulation, and for which potential would not offer that predictive accuracy. But let me show you a couple of other examples I'm very fond of. I talked about the complexity not of the system but of the process. Here is an example. Here we are looking at the prediction of the color of a material. So in the optical limit, what is the reflectivity, how much of the, in this case, solar illumination is absorbed, how much is reflected. And so what you're seeing in the top is the prediction for 3 metal or metal alloys or intermetallics of what should be their color. So the purple one, in case you wonder, is gold aluminum. And this looks funny, but it's actually a very complex problem where you need to understand how photons are going to excite electrons. You have interband excitations, intraband excitation, so you need to calculate your dielectric function, again in the optical limit, and then we know what is the spectral sensitivity of our eyes, and we can transform this calculation in what we see, and the results, as you can see, can be very good. So this is an example of a complex process. Another one that is also a favorite of mine has to do with transport. In this case, we are looking at the resistivity of a monolayer of graphene at different temperature, at different levels of doping. And in general, you see seeing excellent agreement between the prediction on the left and the experiment on the right. But this is very complex. It's multi-scale, it's multi-physics. We need to calculate how electron and phonons interact with each other. We are looking here at the electron-phonon limited regime. So we need to do many-body GW calculation. We need to do density functional perturbation theory for the phonons, for the third-order processes. And then we need to incorporate all of this into a Boltzmann transport equation. And even in something for which at least the theory seems so established, when you dig further and you try to calculate things, you discover that there might be pieces missing. And it was a lot of fun. We worked quite a lot in thermal transport, discovering that actually the Boltzmann transport equation misses, as it had been suspected for a long time, a critical piece that is relevant, especially for fairly disordered or glassy systems, where one has that there can be tunneling of phonon wave packets from one branch to the other in a, say, block picture, or a tunneling between one state to another. And this additional term that you show here as a blue line can become very relevant or even dominant with respect to the green Payals-Boltzmann term in systems that are fairly complex, like in this case, lead perovskite. Okay, so let me go towards the end of this. Let me show you some examples of the power of calculations to discover novel materials. This has been a fun project where we tried to replicate on a computer what Gaiman Novoselov had done in exfoliating with Scotch tape graphite. And so what we did is we took all possible materials and we repeated what was done experimentally. And that's quite typical of all these high throughput efforts. In this case, we have been ingesting experimental databases of inorganic materials, trying to understand if these materials could be exfoliated, and if they were, trying to look for interesting properties. And the challenge that is here is to do this in robust and reliable way, but also in ways that can be shared and disseminated. And so I'll discuss later, but this is an example of just one workflow, one set of calculation where we take a three-dimensional inorganic materials and we do everything that is needed to characterize its electronic state, its ground state. So we ingest it from the database and we transform this into a calculations that then we run in a series of actually reconnaissance calculation to find what is the electronic ground state. Is it insulating? Is it metallic? Is it magnetic? What are its phonons? Is it mechanically stable? So that without any human intervention, we can figure out what the system is, and we can do this in a high throughput, reliable ways for all these materials. We can calculate binding energies. We can figure out if these materials were exfoliable, and all of a sudden, we didn't find only graphene or transition metal dechalcogenides or black phosphorus or, the portfolio of 20 or so two-dimensional materials that were well known, but we actually found thousands of materials that could be exfoliated and that are now really our portfolio of 2D materials to look for interesting properties. Some are listed here. I'll just show you a nice example that was our first effort, that is looking for a quantum spinol insulator. So looking for 2D materials that had a non-trivial Chern invariant. And we found quite a few. We found 14 of these. But the nicest story was actually that we were able to discover that a mineral that was discovered in 2008 in the Amazon by an expedition of a Czech crystallographer, and it was a mercury-based mineral, had actually an electronic band structure that was giving rise to the first ever material that was a Kane-Meillet quantum spinol insulator. That was actually the first model in 2005 of, say, beyond graphene quantum spinol insulator, driven by second nearest neighbor spin-orbit coupling. And you see this is the structure. In particular, it's a material that has a band gap of half an electron volt. So it's a room temperature quantum spinol insulator. And that was enough to get a number of groups excited. And so we had collaborators here in Geneva growing single crystals, doing the characterization, finding this is actually a dual topology material in 3 dimensions. So it has a dual character. And it's just an example of, sort of how you can do, in this case, a novel science, finding the first ever Kane-Meillet quantum spinol insulator with some of these simulations. Okay, let me conclude with some comments, maybe more related to our own center here, Marvel, or also to the Max Center of Excellence, of which Elisa Molinari will be talking in one of the future webinars, but also harking back at what I said about the fact that we are not doing enough to create a digital infrastructure for the very impactful science that I think all our community is doing. And this is, if you want, our own technology stack for this. It's been, in many cases, works of years to build things like AIDA, in this case, that is the entire operating system to manage, automate, persist, and reproduce our calculation. The Jupyter environment to deploy this and to make it available to our collaborators, or to disseminate the data and the simulation services on the web. You can actually go to these websites, aida.net and materialscloud.org, and you'll find a lot of materials. I won't go very much into the detail of this. There are especially 2 papers, but one very recent that describe the entire framework and how we, thought it was needed actually to support this digital infrastructure to build the entire operating system, to take care of the automation that is needed in high throughput, thousands of calculations per day, or in certain cases, we can run tens of thousands of calculations per hour, but in particular, how we can and should store this in the appropriate database that preserves all the links, all the provenance. So every piece of data is actually linked to all the parents and the children. And as scientists, we shouldn't really worry about these technicalities. They should be taken care at the operating system level, and we should work in the green pillar, the environment pillar, where we built the scientific workflows, and we might then want to share our data and our workflow in the appropriate ecosystem. And again, I'll just show you a little bit hint, but you could go to the Materials Cloud website to see how, the entire, in this case, infrastructure to disseminate the data in this section, this archive, explore, discover section. These are actually open. Everyone can submit data, say, to the archive, exactly as you submit preprints to the preprint server, or how we expose simulation services through AIDA Lab. I'll actually show you a brief movie that comes exactly from the Materials Cloud. You could click on the Discover section. In this case, is to the material project. Some of this is very standard these days in computational material science, exposing curated or not curated materials data for the community to browse. I think what is actually quite unique to what we do is that, as I said, every element is part of a directed acyclic graph that you can actually browse. Of course, you could query it, but here you can click and even browse it graphically to understand how every calculation has been done, where it comes from, and what it has given rise to. And I'm almost done. I actually said, we are so fair that actually even Snow White is upset. Let me conclude with the last movie. This is an example of how our experimental collaborators are actually leveraging all of this. This is from the group of Roman Fasel in EMPA, but in particular Daniele Passeroni and Carlo Pignedoli, having built within AIDA Lab all the capabilities to do on-demand, on-the-fly quantum mechanical simulations, density functional theory, GW calculation, image correction, predicting what would have been, say, the result of a transport measurement, IV characteristic, STM images, and all of this becoming available not only to the computational scientists, maybe accelerating their work, but actually to the experimental students that all of a sudden have an expert platform ready to go. Okay, with this, let me finish my conclusion here. I think this is by now a leitmotif, the fact that, materials are really the technology enable that really power our economy and improve our lives and our society. And, I really believe that we are changing the entire paradigm of design and discovery thanks to this combination of first principle simulations coming in from the world of computer science, machine learning, and big data. And I think what is missing and what we really need to think at is really the construction of this open digital infrastructure for the world-class science that at variance with physical infrastructures are available to all. Briefly thanking in particular Marvel and Max, and I leave you with my favorite New Yorker cartoon. Thanks a lot for following.
Okay, thank you very much, Carla, for this broad description of what are the challenges ahead of us in the...
Ignacio, I think you are muted, or at least I can't hear you.
Okay. Can you hear me now? So thank you for the presentation. And now we move to the second presentation on TREX and the leaders of TREX. So this will be shared by Claudia Filippi and Anthony Schemama. So Claudia, I think you will start and then Anthony will continue.
Good. Just give me a second that I go in slide mode. Good. Can you see it?
Yes.
Perfect. Good. Okay. Good. Okay. Well, well, thank you very much for the opportunity to present a new center of excellence in exascale computing, which hasn't started yet. It will start in October. The name is TREX, which stands for targeting real chemical accuracy at the exascale. Okay. So as Ignazio already mentioned, we want to develop, promote, and maintain a platform of open source software, high performance software, with a particular target of quantum chemical calculations and stochastic quantum chemical calculation. So a center of excellence is a consortium of people, and we are having quite a few computational scientists in different fields. So quantum chemistry, of course, condensed matter physics, and also machine learning for quantum problems. Then our consortium also comprises quite a few software and high performance computing experts and a communication SME, as well as a representative of different communities, strong correlation, catalysis, and density functional theory development, actually. So here is a list of partners. So in black are the, let's say, academic institution or research institutes. So, okay, Claudia Filippi, that's me, Anthony Schemama, Michele Casula, Sandro Sorella, Saverio Moroni, we have Aya Lavi, Matus Dubecki, Kasia Pernal, Anatol von Lilienfeld. Then we are having a bunch of more computer science experts, Cedric Valenzi, Pablo Oliveira, and William Yalbi. To Tier Zero Center with Fabio Finito and Dirk Pleiter, so Sineca and Jülich. Then we are having a SME, Megware with Axel Auveter, and finally a communication company with Sarah Pitonet and Silvana Muschel as our, let's say, contacts. Okay, so it's fair to give the name of everybody who is going to be involved. So the focus is very much like the previous talk, quantum mechanical simulation. So we're always in the realm of first principle simulation of material properties. And of course, we heard, let's say, density functional theory is indeed, the method of choice. It can greatly reduce the complexity of the simulation by working directly with the density, which is a three-dimensional object. And there are many success stories. We heard some. You can handle large system, and there's been already a very, let's say, long and coordinated effort in generating community code. Okay, but it works in many, many cases. But there are problematic systems where, or also, let's say, properties across different materials where the approximate treatment of electronic correlation creates a problem, okay? And now the question here is, how can we improve the predictive power of density functional theory? So how can we help them, can we help Nicole and others to actually find the correct function? Okay, so of course you can go back to experiments, but then our predictive power is lost. And in that case, is advisable, we believe, to actually move to accurate simulation. And that's where TREX is coming in. Okay. So now if you are looking for correlated calculations, it means you're going back to the full, let's say, many body wave function, which is a more complicated object. You have in 3n dimensions, where n is a number of electrons, and you're having two lines of attack. Okay, you're having high-end traditional quantum chemistry methods. There are many acronyms and very powerful and very, very nice codes to actually do accurate calculation on systems which are, of course, relatively small compared to what DFT can usually actually tackle. And one of the problems that some of this code, not all, have, and some of this method actually is more methodological even, that they cannot exploit already, petascale systems. So a question which therefore arises, with the move to the exascale is whether we are actually going to lose also some of these communities, okay? And so how can we also bring them, with us to the exascale? And then we are having quantum Monte Carlo techniques, indeed at the core of TREX, where they have many things in common, but they are actually solving the simulation of the quantum interacting problem in a stochastic manner. Okay, so for instance, you're having an integral, so that's an observable, is an expectation value, is an integral, and you can compute, in the simplest flavor of quantum Monte Carlo, you can compute your integral by Monte Carlo techniques, by sampling your integral, okay? So, well, we can do better than that. We can also improve on a given ansatz. And a common feature is that these simulations are definitely much more CPU intensive, okay? They are more CPU intensive than EFT, but we have the, one advantage is that we can surely scale to massive parallelism, okay? Now, that said, I think that over the years, there's been a bit of wrong perception that because we can scale to large system, if you're giving us a big enough computer, we can give you, let's say, an accurate results. And that's not true, okay? So a big computer is not enough. Okay, but then, why quantum Monte Carlo at exascale now? Well, I believe it's a good moment because in the last decade, we'll say maybe 15 years, there's been really a lot of important methodological advances, okay, which are really essentially creating new prospects for these techniques. And I give here two examples. One is the fact that we can finally compute, in a very efficient manner, analytical derivatives of the energy. So we can actually treat the techniques as internally consistent, meaning we can obtain the optimal geometry and the optimal wave function in quantum Monte Carlo. And then finally, we can explore and exploit the freedom, which is at the base of at the core of our techniques, the freedom in the choice of the wave function, this many body wave function. And there's been a lot of developments, for instance, of new functional forms, from Geminas by Sandro Sorella to the Fermi-Net by Matthew Fulks, where he's really essentially simulating a complicated, correlated wave function using neural networks. Okay, and this, can be done also thanks to the stochastic nature of our, let's say, applications. Okay. So to convince you, I will show you essentially 4 examples, which are a bit of a mix of application and development, okay? So this is the computation of efficient derivatives of the energy, in particular interatomic forces. So we are going from a very tiny system, that's butadiene, and then we are scaling up to something which is C60H62, okay? And here what I'm showing is the cost of computing energy plus forces divided by the cost of computing the energy alone. And on the x-axis, what I'm showing is the number of determinants, which in some sense tells us what is the complexity of our wave function, okay? And what we can see is that, as we increase the system, the, let's say the cost of computing the force is only a factor of 3 higher than the cost of computing the energy. And it's actually constant, let's say it doesn't grow as we make the complexity of our wave function large. Okay, so if you're willing to do a QNC calculation, you can now actually compute forces and optimize a structure. Okay. Now, this is a combination of a field, and the power of the techniques, so strong correlation, that's where we can play a role. This is the work by, Casura and Sorella. They were trying to predict the shape of pairing in iron selenide. And so what they did, they use a wave function with a strong pairing, and they fully optimize all parameters, okay? And they actually analyzed the nature of the pairing, whether it's actually a superposition of S and D wave. But this is actually an outcome of the simulation. It's not an input. It's not something you're actually tuning in the functional form, but it's something which really comes out of your calculation, thanks, also to the full optimization of the wave function. Now, another field, which also we want to pursue within TREX, is the study of magnetic interaction in molecular system, okay? So these one are iron-sulfur complexes, where you're having many low-line spin states. They are very relevant in biocatalysis. And what I am here, schematically illustrating is the fact that there is a lot of effort using full configuration interaction QNC, and to actually speed it up by, a compression of the wave function and various other tricks to actually treat, this very, very delicate system, which are actually quite difficult for density functional theory. And then finally, I conclude as an example with non-bonding interactions. This is where we have been working now as a community for quite a few years. And now if you go on the left of the figure, what I'm showing on some borates. These are DFT calculations. This is the only experimentally known. So they are glassy, very porous material. And now what the author have done, have taken various crystals and they have decorated with this unit. And if you're using PBE, which is very, very commonly used functional, you would predict them to be more stable than the actual only experimentally found structure. And if you're putting on, let's say, van der Waals correction, you're going to have a very large shift, both in energy and also in density. Okay, and now what here these people have done, they have essentially zoomed in on a couple of such crystals and done, QNC calculation, also optimizing the structure. So that's also important to actually determine, in some sense, helping, guiding the choice of the appropriate functional for this type of systems. Okay. And on the right-hand side is a very different class of material. So, these are very large buckables in some, with pi-pi interactions. And but also here the goal is a bit the same, is to guide the development actually here of functional for van der Waals interactions. Okay. So, okay, I hope that with this example I convinced you of that indeed, the field has reached a new level of maturity, both in terms of application and of methods, okay? And these methods, these quantum Monte Carlo methods, are at the heart of TREX. And I must say that many developers of the techniques and also of codes are in Europe, okay? And indeed, some of them are part of our consortium. So what about quantum Monte Carlo and exascale? Well, in principle, and then Anthony will elaborate on it, we are a killer app for exascale. I mean, we can run in a mode where we are very CPU intensive, we have small I/O, small memory, little communication, so in principle, we should scale, okay? And the idea is that if you're having all this computational power, we can actually assess system sizes where we are having little competition in accuracy versus efficiency. And so, as I already mentioned, TREX is federating scientists in this general area, and also, quantum chemists, more deterministic quantum chemists, high-performance computing experts, and SMEs. And really, we are trying to unite, this effort, which is now, dispersed in research codes or homemade codes, okay? And to really create a software platform, okay? So now we have discussed a lot what kind of software we want to generate. So we are talking, I'm talking about what we will do, okay? We haven't started yet. And so we decided that we don't want to do a single code, okay? We don't think it's good for the community. We don't want a monolithic code. We want to foster synergy but maintain diversity. So what we want is a platform of independent and interoperable codes. And ideally, this platform is extendable and also operable in combination with codes outside TREX, okay? We want to increase the community. And at the core of the platform is a high-performance library of kernels we call the QNC-KL. And the creation of this library requires a true collaborative effort, because a lot of our codes will be absorbed, which means essentially rewritten and thrown away and replaced by QNC-KL. And we hope, that in this effort, also other people from the community or outside the community will actually join us. Now, what is our software model? As I said, QNC-K library is the core for an easy integration inside TREX, but also external stochastic and non-stochastic codes. We will develop one common input-output library, so we can use, TREX also in a pipeline. That's very common. Not all codes are optimal for a single thing, but also we will have then a single interface to targeted quantum chemical or DFT, also condensed matter codes. Okay, and the idea, for instance, also is to bring along then communities which might not naturally go to the exascale. Of course, in doing so, we will have to refactor and modularize our codes to use both the library and the input-output library. And then finally, let's say the top will be the generation of workflows. Okay, so because QNC, as I said, is usually used in a pipeline, getting input and giving output to other codes, but also for high throughput computing, and also to machine learn the accuracy we have to other techniques. And here actually I'm linking to the previous talk. So for this, we decided to actually build our pipelines, our workflows, inside using actually AIDA, so this is to leverage on a sophisticated informatics project, which is quite a high level of development, but also to foster integration of external codes in TREX platform, as well as transfer our accuracy to these problematic cases I mentioned before, which are a problem for density functional theory. And indeed, in TREX, we're also integrating and further developing machine learning tools. So to conclude, and then Anthony will give more of a computer science perspective on this. So our codes are TurboRVB, CHAMP, and QNC Chem for variational diffusion Monte Carlo. We are having NESI for full configuration interaction Monte Carlo. We are having two deterministic quantum chemical codes, quantum package, which does a CIPSI wave function, and GAM core by Cascia Pernal, which does some quite sophisticated DFT, with multi-reference and things like that. We have in machine learning, so the quantum machine learning package by von Lingenfeld. And finally, in TREX, there are quite a few computer scientists. So we are also going to keep, they will also keep developing performance and optimization tools such as Macao or Verificarlo. And now the second part of the talk will be given by Anthony. So I stop sharing.
Thank you, Claudia. So, okay, I'm trying to share my screen. Can you see my screen? Yes?
Yes, yeah, we
okay,
can.
Perfect. Okay, so I'm going to talk more about the high performance aspects of the project. So we're an exascale project, so I'm just going to give a few words about exascale. So there is a supercomputing race where we are trying to always to be more powerful than we were before. And so if you look, it's the same as Nicola has shown, every 10 years you do like 1,000 times more floating point operations per second. So now I'm going to talk about flops instead of floating point operations. So every time you multiply by 1,000, so it's an exponential law, and every exponential law is doomed to fail because it will go to infinity at some point. So there should be somewhere a crisis. So the crisis is in front of us. So we can see now that Moore's law is ending. So the crisis is not here yet, but we hope that technological breakthrough is going to let us continue this race, and maybe it's going to be quantum computing. We don't know, but still, yet now we're in the beginning of the end of a technology, and things are becoming very complex. So we went to terascale by using distributed parallelism, then to petascale with multi-core chips, and now we're trying to do more, and there is no other way than using hybrid architectures to reach exascale. So exascale, when we talk about exascale, we talk about a measure of performance, which is the number of flops you can do. But we don't talk enough about how the rest is evolving, because when you make an operation on a computer, you're doing a floating point operation, but you need some data to do the operation. If the data is not here, you cannot do the operation. So we need also to consider the memory capacity, the memory bandwidth, latency, I/O network, and all the rest. And if they can improve by 1,000 times, then everything's fine. And if not, then we have problems. So let's just to show you the situation now, let's just do some simple math. Imagine you want to calculate a vector z, which is a plus b times c. And so consider it's huge, it's all in memory, and you want to compute it on a modern CPU. So you take the specifications of your CPU and you see, you just calculate and you see you can get 960 gigaflops per second. Then you take the specifications of the memory on the machine and you see that you can get 128 gigabytes per second. So just by taking the numbers, 128 gigabytes per second means that if you have 128 gigabytes on the machine, in 1 second, you can really transfer the whole RAM to the CPU. It's huge. It's really incredible. But now, if you try to see what kind of operations you can do, then you can divide the number of gigaflops by the memory bandwidth, and this will give you a number which is the number of flops per byte. So this means that when you have fetched some data in the memory, how many floating point operations you need to do with this data so that you will reach the peak performance of the machine. And just this CPU, you know that you will need more than 7.5 floating point operations on a single byte to sustain the peak performance of the machine. And so if we go back to our example, we see here that we have one addition, one multiplication, so it's 2 flops. And in terms of memory operations, we have to load A, we have to load B, we have to load C, and we have to store Z. So we have 4 memory operations, which is 32 bytes. And so the arithmetic intensity is 0.0625 flops per byte, which is very far away from the 7.5 flops here. So with the current CPUs we have, if we do this kind of operation all from memory, we reach less than 1% of the peak of the performance of the CPU. So this shows that these machines are complex, and if you want to reach the full power of these machines, you need to really know how it is organized and how your data will move inside. So I was talking about hybrid architecture. So we are going to have some GPUs or other kinds of accelerators. So will it be better with the GPU? So take the numbers and you look at the GPU. It's the same problem, 6.2 flops per byte. And so it will be also around 1% of this particular operation. So also on GPU, we will have to find some algorithms where the arithmetic intensity is high. So it's going to be difficult. But then there's another problem, is that the link between the memory and the GPU is 64 gigabytes per second. So if you take this number, if you have your data in RAM, you want to go to the GPU and go back to RAM, you need an arithmetic intensity which is even larger. So, and in that case, it will be slower than CPU. So if you want to use properly CPU and GPU, you need to be an expert in the way the machine is built. You need to know lots of things, much more than just a scientist that's knowing Fortran. Okay, so now a few words on QMC. So it's well known that QMC is easily scalable. That's also Claudia has said it's a killer app and everything. So that's true, but to go to exascale, it's not enough, because QMC is scalable, yes, because we can run trivially many trajectories in parallel on the machine, but it will not be easy. And why will it not be easy? Because if we want to go to exascale, we need to be massively parallel and also efficient. If we are 1% of efficiency and we are massively parallel, we'll be petascale, not exascale. So we need to do something to make our calculations more efficient. So efficiency is is quite, well, it's not trivial even with QMC, because if we treat some small systems, we'll have some small matrices, so we'll have low arithmetic intensity. And if we go to very large systems, instead of doing the same linear algebra as small systems, we go to linear scaling algorithms. And in that case, we'll reduce the number of operations and memory access and go to linear scaling for memory and CPU. And in that case, we'll be very low. We'll have very low arithmetic intensity by nature. So it's going to be complicated to find algorithms where we can have where we can push the arithmetic intensity very high. Also, the other way to accelerate simulations is to find some parallelism within a trajectory. That's the only way we're going to reach exascale, because DMC trajectories need to be ergodic in order to have a correct result. So they need to go far enough, and if the system is large, we need to accelerate the trajectories, each trajectory one by one, such that it goes far enough. And a QMC trajectory is sequential by nature, so finding parallelism inside is not trivial. And the second point where it's going to be difficult is that one trajectory has to perform a very large number of steps to be ergodic. And one step should be in the order of the millisecond in the wall clock time. And in such a time scale, communications will be very problematic. So exploiting parallelism to improve the efficiency of one QMC trajectory is a difficult problem. Okay, so a few words about our software development model. So progress in quantum chemistry may require some new codes with new ideas. And these new ideas are developed by physicists and chemists, scientists, and exascale machines will be horribly complex. So the question is it reasonable to ask these scientists and these chemists, physicists to write codes for exascale machines? And here is an example of code that is supposed to be efficient on exascale architectures. So it's a code which is just doing vector addition. It's the same as what I've shown before, is z equals a plus a times x plus y. It's the same kind of problem, but you see that you have to. I don't think many physicists and chemists are able to write such code today. So there's a big problem. So my answer is it's not reasonable to ask the scientists to write this kind of codes. So the dream is to have a machine where the scientist here will write just normal Fortran as he or she does every day. And then it would be nice to have a compiler there that's going to transform this code into this very complex code. So a compiler, I put the definition here, is just a translator between one language to another one. And the problem is that artificial intelligence is not ready yet to do this kind of transformations. It's too complex, so we don't have the compilers that are able to take a naive code and transform it in high performance code. So since we don't have, since artificial intelligence is not ready, we still have natural intelligence, which is in this case superior to the machine. So we have here a human that's going to take some code written by the scientists and transform it into code for the machine. So this we know how to do today, this kind of transformations. And so we can consider that this person here is like a biocompiler. It's a human layer between the scientist and the high performance code. So, so if we are in this model, we see that doing the biocompilation of a code is going to be expensive because it will you will have people doing this work. It's going to be complicated, and so this will need some interaction between the scientist and the H.P.C expert to talk together and agree in such a way that this person here will have will be able to do the work easily, and so we'll have to coordinate with these people, and we'll have also to isolate all the parts of the different codes. We have to put them together such that we'll do this transformation only once. So that's why we want to create the Quantum Monte Carlo kernel library, QMCKL. So first we'll identify the common kernels of QMC codes of TREX. then agree on an API, application programming interface, with scientists and H.P.C. experts. We'll give the freedom to the library to handle the data movement between the accelerators, between the memory. We'll build the library in such a way that all this will be handled by the library, such that the scientists will not have to worry about where is my data? Is it on GPU? Is it on CPU? Is it in RAM, in cache, and everywhere? We don't want the scientists to care about these problems. And so to do this, the scientists will, once we have the application programming interface, the scientists will just propose a simple implementation of their algorithms that will be very easy to read and that will compile. So we'll have a low performance library, but which will be very easy to read. And so we'll compile our codes and link with it. And at the same time, the H.P.C. experts will biocompile it in high performance implementations. And then all these libraries will be integrated in the TREX codes, and all our codes will be fast and efficient. So that's what we hope. So it's not what I'm telling you is not very new, because it's an old practice where there were many successful projects. If you take Blas and Lapac, for example, it's one of the best examples. Now, if you have a scientist who is doing some linear algebra in a code, you say, no, don't write a matrix product yourself. Just call Blas and Lapac, is going to be efficient. And then on any machine is going to be efficient. So that's the kind of design we want to use. So the benefits for scientists. So the first one is that we don't impose scientists to write in a particular language, because this is problematic. If you want to, if a scientist wants to write in Python, in Fortran, in whatever, it's going to be possible, because our library will be callable in any language. And then if there is no complexity related to hardware in our codes, then the code will not die when the architecture changes. What will die is probably the implementation of the high performance library, but then we will re-implement it for another architecture later. And scientists will never have to manipulate low-level H.P.C. codes, and H.P.C. experts will not be required to be experts in theoretical physics. So I think it can be a very successful model. So QMC can scale easily, yes, but if we can efficiently compute one trajectory, and so the QMC KL we're trying to design will be an answer to this problem, to really be able to use the hardware to accelerate the realization of one trajectory, and then we trivially massively parallelize over trajectories. Thank you.
Okay, thank you very much, Claudia and Anthony, for this thorough introduction to TREX and the computational challenges. And now we move to the last presentation by Julia Galli, related to Mecon. So Julia, now it's your turn.
You can see my screen, right?
Yes, we can.
Okay, all right. Good afternoon, and thanks to Ignazio and Sarah for organizing this webinar and inviting me here. Very glad to be here. So I will share with you some thoughts about the difficulties, in a way, and the opportunities in predicting and designing materials and molecular properties through computation. And Nicola started his talk by showing a map of the Earth. And I will actually start mine by showing a map of the Middle Earth. So for those of you who are not, Lord of the Ring aficionados or Hobbit aficionados, just think about a map of a difficult and rugged landscape that you want to navigate. So the goal, as it has been stated by the two previous speakers, and the topic of this webinar, is to understand how to do materials prediction and design, and using high performance computation, high performance architecture, and going towards the exascale. So there are different classes of materials that people are interested in, and we in particular are interested in materials for energy and also for quantum information technology. So if you are able to actually make prediction about material that may be useful for novel computing and also sensing devices, and if you learn how to do real quantum simulation on quantum computers, then you can go back again and change the way of doing materials prediction and design. And by this hybrid model, you can make, innovative contribution to material science and in general also condensed matter physics and quantum chemistry. So what I would like to do this morning in the next 30 minutes is to tell you about a theoretical and computational strategy that within this general vision we are adopting to look at materials prediction and design. And of course, it's a small part of a much bigger vision that Nicola has highlighted at the beginning. I will give you two examples where I will try to point out the challenges that we are facing in energy and quantum information technology. And I will close with a simple yet challenging simulation on a quantum computer. So when we, of course, this is, as I said, part of the bigger vision, and it's a one sub-strategy to look at material simulation. So the very first question are structural properties. How do you determine structural properties? And what we do when we look at this problem, usually we do, and by we, I mean within our center, MICOM, funded by DOE in the United States, we do first principle simulation augmented by atomistic simulation to look at the properties of materials. And recently we have embarked in an effort that many other people are, of course, embark into in coupling our first principle simulation with the advanced sampling. Now, if you want to characterize material, of course, you need spectroscopy. And a spectroscopy is usually done with what I call post-DFT methods based on many-body perturbation theory and beyond the DFT. And we have been involved for quite some time in developing some of these methods. And because we are interested in quantum information science application, we also are interested in looking at spin dynamics and looking at spin spectroscopy of materials. And I'll give you an example in a little bit. And so what I call advanced characterization is a combination of spectroscopic method and also spin dynamics calculation with model spin Hamiltonian that I will tell you in a little bit. So here I'm mentioning the codes that are either developed or used within our center: QBox for first principle molecular dynamics simulation, SAGES for free energy landscape, WEST coupled with Quantum Espresso and QBox for advanced spectroscopy. And I think that, of course, here I'm preaching to the choir, saying that verified, validated, and optimized codes are key to successful prediction and innovation. And our philosophy is that these codes should be open to the public and coupling together to the community and coupled together as much as we can to form a innovative ecosystem. Of course, when you talk about DFT, you always have to ask yourself which DFT you're using. And there is incredible amount of work out there, and in the last 30 years ago, to address exactly this question. And here I'm just mentioning some work that we have been involved in trying to address this question for specific material lately, and some work that we have done recently to couple advanced sampling in a hierarchical manner with density functional theory to look at materials. So if you want, and if you are not thinking about high throughputs calculation, but you are addressing problems of specific material, this combination of first principle molecular dynamics and advanced sampling is the first step that you do to get structural models. And of course, structural models will be characterized by spectroscopic methods, and by going back and forth, they will be refined. So one of the challenges that we are still facing is to really be able to do in operando spectroscopy, both in silicon and in vivo. We have built, and now not only we in the center that I'm talking about, but we as a community at large, we have built a number of very powerful and interesting techniques. However, given the capabilities that we have today, we are not yet there to do in operando spectroscopy really connected with experimentally and on the fly, but we are getting there, and I see this as one of the challenges and opportunity of our field. Our contribution to this has been to look with post-DFT methods on to make some of the method to do on-the-fly spectroscopy efficient and deployable for very large system. And by large system, I mean system with up to 1,000 of atoms. And of course, when I talk to my colleagues doing classical molecular dynamics, these are not large system for them. One unifying kind of methodologies that we are pursuing these days to look spectroscopy at finite temperature, both electronic and optical and vibrational, is to do molecular dynamics in finite field by coupling in client server mode, first principle MD codes and GW and BSC codes to obtain the electronic screening from final field calculation, and hence do calculation for optical properties, but also for vibrational properties by computing polarization and polarizabilities on the fly. So let me tell you with this kind of strategy, what are we able to do for some problems that are difficult and I claim important problems in material science. And one is, for example, what I call the puzzle of water splitting. So suppose that you want to understand how to optimize, optimize material, but also find new materials that are good electrodes that you want to put in water to split water, to do fuel generation. Well, you need to be able to compute a number of properties. And also, and this point was also made in Nicola's talk, you need to be able to understand many processes. And this is what this arrow here is supposed to be telling you, that if you want to understand that problem, you need to have a handle on aqueous interfaces, photoexcitation properties, and so on and so forth. And let me just go through this rapidly, telling you some of the things that we have been looking at. And of course, we are not the only one, and I'm just taking our work as an example here. So first of all, you need to understand, if you want to split water, the electronic properties of pure and salty water. And then, of course, aqueous interfaces are very important. And actually, aqueous interfaces are quite complex, because usually you have a material that absorbs light for you, but then you need a catalyst. You need a catalyst on this material. And this is, the reason is simple, because we haven't found yet a material that can absorb light and be a good catalyst at the same time. And then you have very complex interfaces, and you have to worry about even the morphology of interfaces. And even if you cannot completely from scratch look at the morphology and active sites, first principle simulation, if you control the accuracy of the simulation, can give you very, very valuable information. And these are just two of the examples out there taken by our work. Then, of course, you want to split water, you want to absorb light, and you want to transport charges. And the problem of charge transport is a very complicated one. And if you want to do electrochemistry, you should be able to do spectroscopy of interfaces under bias. And my claim here is that even if this remains a big puzzle, we haven't put all the pieces of the puzzle together. We are certainly not yet able to do high throughput for all the pieces of this puzzle. I think that this is a problem where the contribution of first principle simulation, especially, the coupling of ab initio molecular dynamics with spectroscopic method, has contributed to progress in the field, to the point that really now there are a lot of experimental studies that are done very, very close collaboration with computational study, because computation has acquired a prominent role in this very important energy problem. Okay, so let me switch gears a little bit and give you another example, which is related to what the first example that I told you about in my first Middle Earth slide, which is materials for novel computing and sensing devices. And here again, I am restricting my attention to a specific class of materials, and these are spin defects. So atomic point defects in 3D and 2D semiconductors and insulator that we want to optically address. So we have a solid, we want to create a defect. This is a kind of localized environment that you want to use as a qubit. And probably the most famous one of these point defects for the use in solid state quantum information technologies, the nitrogen vacancy in diamond. And if you want to actually use this defect and initialize it, manipulate it, and you do readout, and you want to create a robust two-level system that will be your qubit, you need to satisfy a number of requirements. And of course, I'm not going through all these requirements right now in any detail, but this is just to tell you that, starting 10 years ago or so, the kind of requirement that one needs to create these two-level system to use a qubit were quite clear. And so given those requirements, you need to understand the optical properties of these defects. You need to understand the coherence time. You need to understand whether you can entangle two qubits and whether the coherence time can be such that they will allow you to do either computation or sensing. And then there are a number of other requirements that I am not going to explain in detail today. So this is one defect that is still being pursued in a very expensive material like diamond. And there are several questions, interesting questions that one can address. And one is, can we find an analog of this qubit, for example, with other materials that are cheaper and easier to make, but also other materials that may have other properties that we may want to exploit, like piezoelectric materials. And here we and several others, actually I should say many others, have used the first principle calculation at different level of accuracy to address exactly this question. Can we actually find other materials? And this is an example of where we have looked at what happens when you take silicon carbide, which is very much studied by experimentalists today. It's a much cheaper material and easier to do to make than diamond. And we have asked the question, what happens if you put ions, large transition metal ions in this material, and can you exert a chemical pressure and modify the properties of the material to have a qubit? And the answer is yes, of course. There are, otherwise I wouldn't be talking about this. There are conditions that you can create by using chemical pressure. And likewise, you can, with strain, stabilize configuration of a defect that are satisfying all the requirements that I flashed at the beginning to make the defects that you want. And while doing this, we learn how to study the coupling between spin in the material and to look at the coupling between spin mechanical coupling in the material. By we have learned, I mean, we have learned to do, and of course, I mean, the basic theory was known, but we have added some understanding and also some efficiency to how calculations were done, so as to not only explain experiment, but also predict properties of what defects may be doing in your material. And this brings me to the next question. Can we predict good defects in addition to property of defects already realized experimentally? So in this field, there is still a huge need, don't get me wrong, of interpreting experiments. Experiments are complex, and in just being able to interpret experiments, and if we were able to do this in a feedback loop with the experimentalists more efficient, would be a absolutely great achievement. But there is also the need of predict other defects in addition to those already realized experimentally. And one thing that we and others, of course, are trying to understand is the following. Can we do a calculation and really create defects and see how they form in a material by, for example, coupling first principle molecular dynamics and enhanced sampling, and understand when you quench the material, what are the defects that form? Or even better, can we understand the quenching conditions so that we form the defects that we want? So this is really getting to engineering a material from first principles. Can we do this directly with first principle molecular dynamics? No, we can't. And so one direction that we are thinking of going into is to have ab initio force field, for example, machine learned and refined through spectroscopy, so that we can do this kind of analysis, and then, of course, analyze the electronic properties. So this is a project that we have and other people have. We haven't been able to do this yet at the level of completely exploring the landscape. However, we have been able to explore this landscape with some empirical potential that have shown to us the power of really trying to understand how to quench defects in order to find new defects with new properties. So as I told you, the property of the defects are structural properties and electronic and optical properties. You want to be able to have a two-level system with certain excitation property, with some difference in energy levels. The other thing you need is to predict a defect that has a coherence time, so that the interaction of your spin in the electronic part of your system is not completely, the coherence is not completely ruined, for example, by the interaction with the ions. And so to address this problem, and I apologize because here there is a very long formula, one way to address this problem is to set up a spin Hamiltonian that describes the interaction of your spin qubit with the environment of the ions, to compute from first principle the input parameters of this spin Hamiltonian, and then to do spin dynamics by evolving the spin density matrix. So this is one way of doing, the coupling between your structure of the defects, electronic structure at different level, DFT or post-DFT, all the way to having your Hamiltonian using those input parameters to look at the evolution of the spin density matrix. And there are several methods, and one is the cluster correlation expansion that we have used, but I'm not going to talk about this in any detail. So can we be predictive? So one thing that I'm not showing to you is that by using this kind of spin Hamiltonian methods, we have been able to reproduce experiment and to also explain what happens in certain experiment. And this has been done, for example, in the system that I mentioned earlier, like silicon carbide. Here, I'm mentioning a prediction for 2D materials where this coherence time that I have not really defined for you, but it's an important property if you want to have a defect, has been computed for a 2D material, molybdenum sulfide, as a function of the number of layers that you have in the material. And we have been able to understand a number of things. For example, that isotopic purification is much more effective in 2D than in three-dimensional system, leading to exceptionally long coherence times. So we have been very excited about this result, and the experimentalists also have been very excited, except that after doing this calculation, of course, we asked the question, what's the effect of the environment of the 2D system that we are looking at? And, the effect of the environment actually is quite substantial. And also it depends which environment. So these exceptionally long coherence time, they're still long, but, you need to include the effect of the environment. And this is work in progress that we're doing right now. So let me go to the last topic that I want to talk about today, which is quantum embedding and simulation on a quantum computer. So getting interested in defects got us thinking about really what about embedding our defect into the solid outside where the defect is, and what about considering only the active space related to the state of the defects and being able to study directly this active space without considering explicitly all the electronic states of the environment. Well, this, of course, is not a new idea. I mean, it's an idea which has been there for quite a long time, and it's an idea that it's at the basis of, for example, dynamical mean field theory and many other embedding theory. And so when we were thinking about this, we thought about two requirements that we wanted to meet. One, we wanted to be able to do large systems, and not only as a defect in a unit cell, but we wanted to do large system. And also we needed to take into account a lot of effects that in other theory were discarded. And one of those, and this is very technical, is the exchange correlation kernel. Why did we get to this problem? The reason why we got to this problem is that if you want to create a qubit with the sum of the defects that I talked about in silicon carbide and in aluminum nitride, people realized before us that these systems are actually strongly correlated. Just by doing DFT and just by looking at the property of DFT of your defect, you will not be accurate enough. And actually some of the states you will not be able to compute. So what we decided to do is to, based on constrained RPA for the expert in the audience, to construct a quantum embedding theory where we have an active space associated to the defects, and the effect of the environment on the active space is determined by computing a dielectric screening of the environment. How are we doing this? We are building on our expertise in computing dielectric screening that we have learned doing GW calculation in finite field for some time. So if you do this, then you can build a Hamiltonian for the electronic structure of the active region, for which you can do either full CI, or you can run this Hamiltonian on a quantum computer. Of course, full CI has a problem of scalability on a classical architecture, and on a quantum computer, by using the algorithm that have been developed so far, and of course there will be more in the future, the system should become much more scalable. And this is just there, and the definition of this Hamiltonian, in case some people have questions. And this is, again, summarizing how we built this quantum embedding theory on the knowledge that we were able to obtain by doing calculation based on many-body perturbation theory. So these are some of the defects that we have looked at, and we have predicted energy level that could not be described within mean field theory, and we were able to interpret and explain several experimental results. So from the point of view of understanding the material, this has been definitely a progress, because you cannot get there and understand what's going on, especially when you have certain type of defects based on transition metal in your system. And these were defects both in diamond and silicon carbide. So next question is, can we actually run this Hamiltonian? We have done here, these are calculations obtained on a classical computer doing full configuration interaction. Can we do a calculation on a quantum computer? And the answer is yes. We did a calculation on using a quantum simulator, and this is the orange line that you see on the right-hand side of your screen. And the blue line, and on a quantum computer, and this is a quantum computing calculation using IBM Q and Qiskit developed by IBM. So what is this calculation telling you? Well, first of all, it is telling you that indeed we can run on a quantum simulator. We can go all the way of having a hybrid kind of calculation where we do a large-scale calculation on a classical computer to understand most of the property of our defects, and then we translate this and we use for the coupling pi SCF. We translate this into a Hamiltonian that we can then run on a quantum computer, and we obtain exactly the same results by using the quantum simulator and full configuration interaction on a classical computer. So this is a validation using a quantum computer of our classical results, or actually I would say the other way around. Then when you use a quantum computer, you have noise in your result. A quantum computer is noisy, and instead of the blue line, you get the orange line for your defect, and still a sizable error that comes from the noise. And this is, of course, where the challenges now are, to try to understand how to deal with this noise and how to improve this noise. If you don't improve this level of noise, you will not make progress using quantum computation for material science. Okay, so let me give you my outlook, and now I'm going back to classical machines. And this is a paper that just appeared in Science by Lyerson and other people asking themselves what's after Moore's law. And so this is the claim of the paper. And the claim of the paper is that in the post-Moore era, improvement in computing power will come from technologies at the top of the computing stack. And at the top of the computing stack, there is software and algorithms. and they will not come from those at the bottom reversing the historical trend. Of course, I need to be super careful in making any kind of buying in this statement, because our own funding agencies are very much pushing the hardware part of the picture, which is going towards exascale computation. And I think that it's very much worth going into that direction too, and looking also at the new hardware. But what I want to say here with this outlook is that, especially for students that may be entering this field, that it's very important to put a lot of attention and a lot of effort in developing new algorithm, in developing new ways of solving the equation that we are all trying to solve, and certainly putting an effort in making our software more efficient, interoperable. I think that all the speakers here this morning have made this point loud and clear. Anyway, if you read this paper, there are a lot of statesmen in this paper that also highlight the challenges related to making progress in software, and it's a very, very interesting, and I'm sure it will become a controversial paper. Okay, I would like to stop here and thank the funding agencies that fund the center that I'm part of, MICOM, and also other funding agencies like the Air Force and National Science Foundation that fund our work. And my group and all the MICOM collaborators, and also the group of David Ashelom in Chicago, with whom we are actively working on understanding and also predicting defects for qubits. And again, thanks Ignacio and Sarah for inviting me here, and everybody this morning for being here. Thank you.
Thank you very much, Julia, for this interesting talk. And thank you to all the speakers that we had today. So my job is that to introduce and moderate the question and answer session based on the chat and input from our viewers. Now, today, it's either a very, very simple task or a very, very difficult task, because the chat has been unusual in that we have got some rather intriguing statements that might be interesting to discuss in front of a glass of wine or a coffee, but from which I cannot really extract a question. We've had one question that has reached us via email. I will share it with our speakers in a second. And so what I propose is that I start with this question, and maybe we could give the opportunities to the speakers to ask questions to each other, so that I can gain a little bit of time to see if someone comes up with new questions on the chat. And I am sure that in any case, it's going to be a very, very interesting discussion for everybody. Okay, so the question that we got is for Anthony, and it's quite technical. Stefan would like to know if there are any attempts at creating compilers that can convert a script from one programming language to another.
Oh, yes, it exists, and it's a very active work. So, the people who are working with us, the H.P.C experts in TREX, the people in University of Versailles, they are working on tools to help the developers to write efficient code. So, for example, the scientists will write a simple loop in Fortran or C, and their tools will make loop transformations and insert parallelism inside to transform it in H.P.C code. So it's an active work. It works on parts of the program, and it requires also for the person writing the code to go back and forth and see what the program has produced to transform the code, accept or reject transformations. But it's not ready yet, but I'm sure in a few years we'll be there.
Thank you, Anthony. If you have some material, some links or something, could you please send them to us so then I can relay them to the person who has asked the question?
Okay.
or publish them on the SICAM webpage for these webinars so that we can share the information. So we have got one question from Fabio Finito. Ciao, Fabio. Which is a broad enough question that I can ask it to all panelists. And that is, okay, so what is the intriguing scientific challenge that you guys expect to be able to solve thanks to the new machines that are coming, something that you cannot do today and hope to be able to do tomorrow using these exascale computers? Vanilla question, but I think very relevant. Claudia, would you like to start, or anybody wants to start?
Well, I mean, Claudia, are you starting? Oh, yeah.
Go, Julia. Claudia will start. We'll follow.
I think that we have all tried to highlight broad classes of problems, and I think that problems related to energy, and so Nicola has talked about thermal transport, and I talked about fuel, and maybe he talked about this as well. So there are a number of problems related to optimizing earth abundant material and efficient material for renewable energy sources that we are far, far, far from having solved, both by looking at specific material and also by high throughput. We have laid in some instances the foundation for doing that, and I think that there are, we will be able to make great progress by using high performance architecture that are coming out, and also, in my opinion, for materials for quantum information technologies. But there are many other categories, and somebody maybe would like to chime in. And in my opinion, the challenge is to be able to link and compute multiple properties at the same time and use these multiple properties in the design and optimization process. And hopefully these machines will help us with that.
Thank you, Julia. Claudia, you were about to say something?
Well, as Fabio knows, since he's in TREX, well, okay, so as Julia said, there are classes of properties we would like to address in classes of materials. For instance, in TREX, we're having some aims at looking also fundamental properties of strong equality system. For instance, describing the different magnetic phases. Personally, I'm very interested in photochemistry. So really describing the response of molecular system to light, where objectively there are really not very methods out there which can do it. And okay, so we're having experimentalists who are trying to design new dyes, and okay, we can describe absorption quite well, for instance, but describing really what's happening in the relaxation is extremely challenging, and input to understand what is the product and things like that would be extremely useful, also at a higher level of calculations. And then okay, I let the word to somebody else.
Maybe Nicola, you can bring the Marvel point of view.
Yeah, I'll use Maria Callas, that was a very famous DFT expert. And there is this story, I don't know if it's true or not, but somehow an admirer entering her room and congratulating her for all the beautiful flowers that were in that room. So, you can imagine the opera diva full of flowers. And she says, well, I have enough flowers. What is missing is that single rose on the side of my bed. And with that, it was, she was meaning I'm missing that something special. And, to answer Fabio's question, I would say, it would be nice. There have been very few paradigm changing materials that have been, discovered by the entire scientific society in the last 30, 40 years. You could think maybe at, the cathodes for lithium-ion batteries, you can think of the nitrides for LEDs, or maybe some of the OLEDs and light-emitting polymers. Maybe we can think of the giant magnetoresistance, but at the end, not that many. It would be great to have that single example that came first from a computation and that is really paradigm changing. I think there have been a lot of examples where computation were involved and were important, but having something that clearly came from that computation and has had a major technological impact, that would be great. And maybe this new architecture will allow us the accuracy and the speed to find that single rose.
Thank you. We have received another question for Anthony. This is again technical on coding and machines, and the question is, could you say something about the reasons why you think that artificial intelligence will not be able or cannot at the moment transform normal code into H.P.C proficient code?
Yes. So I really believe that it's going to be possible in the near future, because it's amazing what they can do with artificial intelligence nowadays. But this doesn't exist yet. I mean, we don't have now. I mean, if it existed, we would have it and we would use it for exascale machines. So the thing is that the exascale machines are being built right now. So we don't have really. I mean, we don't have all the exact specifications of, for example, the European machines we're going to have. We know what they are going to be. So we don't know which choices we'll have to make. And but I'm pretty sure that it's going to be possible to really improve things, code transformations with artificial intelligence. I hope it answers your question.
I hope so too. We will see if we have some more feedback. Okay, so here is a question that is more broadly oriented, I think. So how important do our speakers feel that physics-informed algorithms, so algorithms that can take advantage of physics-motivated numerics and algorithms depending on different systems, will be as we come to the exascale era? Nicola, maybe you can have a first go at it.
Thank you.
My pleasure.
So, but the part I was maybe not understanding, because this question could have two answers. I mean, the physics-informed algorithms, there is one way in which I actually think at what Julia had been describing, that is quantum computing, if you want. That quantum computing is a new paradigm in computation that is driven by physics. And I don't know if the question was about this, or if the question was about injecting, our physics intelligence in understanding, novel material properties. I'll answer this second part because that's the one I know how to answer.
Very good.
And I leave my wonderful, co-speakers to answer the first question. And I think, one thing that I've been fascinated for quite some time has been, how much, say, density functional theory has changed the way we do computation by taking a very simple idea, sort of turning quantum mechanics on its toes, and, starting not from the wave function that was Schrödinger idea, but from the charge density. And that, sort of intuition has allowed to say we are going to, deal with the quantum mechanical problem as a functional minimization problem rather than a differential equation problem. And I apologize to Claudia and Anthony already because, sort of they are doing the very tough differential equation problem. And so in this sense, I keep asking myself, why did we stop there with functional theories? Why don't we build functional theories that are more complex, but at the same time, capture more complex physics? And of course, you know, a great idea was reduce second order density matrix. You can write a energy functional explicitly in terms of data, but you don't know where to search. So there has been, you know, some progress, but, you know, in many ways, ever since it was formulated, you know, more than 40, 50 years ago, we know the function, but we don't know where to search. And my own drive and the things that have been fascinating for me is trying to build dynamical theories with a functional approach, a little bit, you know, trying to replace what diagrammatic theories like GW do, that is, they build a model for self-energies that are maybe non-local, they are frequency dependent. By doing that, they can access properties that are not there in density functional theory. They can calculate, let's say, charged excitation. But my question for a long while has been, can we build functionals that are more complex than functionals of the density, but much, much simpler than diagrammatic expansions, and to capture more physics than, say, density functional theory does?
Thank you. Just a comment. I think that this is a fascinating question also in the field of classical molecular dynamics. All the classical molecular density functional theory based methods that are present in our community, I think, pose more or less the same question in a different framework. Maybe, Giulia, since you have been talking about quantum computing, there is a question about the fact that some branch and bound approaches appear to be more efficient than quantum computing per se. And so the question is, do you think that the future will be somewhere in between IA approaches and quantum approaches? I assume it's artificial intelligence spelled backwards. If not, I apologize, and please correct me in the chat.
Yeah, thanks for the question. You know, the real answer is that I don't know, but I think that there will not. So quantum computing is, of course, a disruptive change, but certainly it's not that you know, one day we will all transition en masse to quantum computing and we will be using only quantum computing. There will be a hybrid model in using high performance architecture as we know it now, and as it will come up in a few years at the exascale, in using also this architecture to use AI methods, coupled with what you can do differently on a quantum computer. So there will be hybrid methods. For us, the motivation to try and use a quantum computer was, you know, the first motivation was really to try and understand whether we could use it and whether it was worth running an algorithm that was not scalable, that we know it's not scalable as of now on a classical computer, on a quantum computer, and look at the scalability. We haven't looked at the scalability yet, because right there, we encounter the problems that many people are encountering running on a quantum computer of noise and on mitigating noise, and now we have to address this problem. But certainly, I don't think that there will be a first order phase transition where we will go from classical to quantum. There will be hybrid way of addressing problems. And also, you know, the question is, there are algorithms that are more efficient on a classical and other on a quantum computer. Remember that to understand materials property and to do prediction and design, you need to address many property, compute many property, and then solve a number of different equations. And so it will, you know, depend. Some equation and some algorithm will be for a certain time more efficient on a classical computer, another on a quantum computer. So it will not just be deciding for one algorithm where this is more efficient. It's a much more complex problem, as I'm sure the person who asked the question knows that.
Thank you, Giulia. So I think we are approaching, or have just passed the 2 hours mark. So Ignacio, did you see questions that I neglected? Would you like to ask a question?
No, but I mean, I think we more or less cover the issues that came out. I had the curiosity, and again, in principle, it's directed to Claudia. I don't know if it has also affected other speakers, because you mentioned about the potential of QMC, Quantum Monte Carlo, in the exascale, and the difference in scale with respect to traditional quantum chemistry approaches. So, would you think that this is really one is challenging the other? So you expect that?
No.
You think that Quantum Monte Carlo can overrule other?
No, no, I wouldn't put no, I wouldn't try. I wouldn't put it in this way. No, I wouldn't say so. I mean, so there are well, there are different regime of applicability, and there are also techniques in quantum chemistry where they are trying to scale to massive parallelism, like like couple cluster. So we are not the only one. Trying to exploit, these machines, and I wouldn't put one against the other. So I think, as I said, also QMC code are operated in combination with other codes, so they are operated in combination with quantum chemistry code, which might provide an initial input, which we then elaborate and optimize. And so I would view it more as a marriage. And, in some sense, some codes, which are beautiful codes and minor scale, they will come with us to exascale in these, within our platform. So I would not create this confrontation between different fields. Yeah.
Maybe to finish, a more general question just for all of you. I mean, this example of the potential of artificial intelligence, as Anthony brought in terms of creating this, producing the code from H.P.C. I mean, we have been talking about exascale, and we have been talking about new algorithms in this context. Coming back to the comment by Nicole about whether we take or not digital challenge seriously, do you see then the development, and beyond having this new H.P.C landscape, do you think that the development of new qualitatively different tools like AI or AI combined with these quantum computers can change qualitatively the way in which we do or we exploit simulations for materials research?
Sorry, before someone answers, I would just like to complement this question with another one that we just received via email, simply because I like it too much to drop it, which is, when we teach in our relationship with students, how do we go about maintaining the balance between the fact that what drives us are the scientific questions and not so much the tools, or not so much maybe the correlations, but the causality? Is this still true? So is it still relevant? And if so, how do we maintain the emphasis on the need to focus on scientific problems as we are confronted with growingly complex environments that are enablers, but maybe also things that distract us? Sorry, big questions, I know, but...
Can I answer?
Anthony, why don't you start? Yes.
So the point is that what is driving the technology is, I would say, video games and artificial intelligence. Where there is money, they will invest in technology. And there's not much money in science for science. So we are not the people who decide what kind of computers we're going to have. Because if we had to decide, we would have chosen something else. Because here we see it's going to be very complicated to program. So we have the technology that's done for very specific applications, and we as scientists need to think how our problems are going to fit on those machines. And so Claudia has cited this example of using wave functions expressed as neural networks. It's very nice because now we have the technology to do very efficient computation on neural networks. So let's use this technology for our calculations and express our wave functions as neural networks. So that's how we have to, well, we do science for science because we do some fundamental research, but we also need to think about what are the algorithms that will work. And because if we really think with pen and paper, we will be very limited to small problems.
Comments on this last question or on what Anthony just said? Nicola.
I wanted to dive in on the artificial intelligence and the quantum computing, and I find it very interesting actually that, a very forward-looking company like IBM, has these two as their pillars, and I think, artificial intelligence as the money-making strategy and quantum computing as the high risk, but also the edging strategy to make sure that they are not overcome by anyone else. To me, artificial intelligence is actually much closer to being relevant, and especially to being enabled by exascale architectures, by exascale not only in a single machine, but exascale on the cloud, by neuromorphic computing, and that is certainly going to change. First, in small ways, how we do research. I mean, we have seen all this, machine learning, the potential, the kernel regression, but more and more how we interpret our experiments. We'll be able to do, get so much data from experiments that only artificial intelligence will capture if there is anything interesting. And the next step is how that will affect our own educational and cognitive perspective. For which, I'm a pessimist. I teach my students that, all these, silicon technologies that we have developed, what have they given us at the end? TikTok. And so, the big question is, what will all this new technology give you? I'll shut up in a moment, but I would recommend for everyone a movie from one of the Coen brothers, and it's called Idiocracy, and it tells about human society in 500 years from now.
If there are no other comments, maybe I would like to counter Nicola's suggestion and point of view with one that I find interesting. I am not sure that I agree with everything, but there is a book written by Alessandro Baricco, which is called The Game, that talks about the way in which this kind of technology is in fact a product of human intelligence and simply manifests a different way of human intelligence to act, live, and be productive than the one that we are perhaps more used to. Now, I am not sure that I agree with what is written in this book, but maybe because of that, I think it's an interesting one that might be a good parallel to maybe imagine a slightly different future from the one that Nicola was proposing. Okay, I apologize if I have neglected questions. I don't think so. I hope not. If we have, we'll try to go back to them via email exchanges if our speakers will be kind enough to indulge us for a few more minutes with this type of things. And for the rest, I think that it's time to say thank you again to the speakers. Thank you to everybody who has been following us for this first webinar of this new series. And Ignacio, maybe you want to conclude.
Yeah, no, I just simply again, thank again the speakers for your time and for your contributions that I think have been very insightful, and for this discussion that has been transversal, and I think it will be useful. And I simply wanted to finish by also thanking all the people who have joined us in this new webinar series, and remind you that all the lectures and the Q&A will be updated, will stay in the YouTube channel and also on our second webpage. And next Thursday we'll have the second session of this series, and I hope you to see you again and to meet on Thursday, 25th. Thank you very much. Bye.
Good evening. Bye.